This week is all about solving systems of equations using determinants. Specifically, calculating the inverse of a matrix and using Cramer's method. But first things first, if you remember, we've already calculated the inverse of matrices. The inverse of a matrix is calculated using this formula, where this here is the determinant of a matrix, and this here is the adjoint matrix. The process in which to calculate determinant calculate the inverse is first calculate determinant. If your determinant isn't equal to 0, you can go ahead and move forward. If it's not, then you can't. But once you do that, you can go ahead and find the adjoint and then put it together. So a little bit of review for a 2x2. Let's say A looks like this. The determinant of A is my little fish. So these numbers minus these numbers. So 1 times -4 minus 6 times 3. Or -4 minus 18, or -22. Okay, that number is not equal to 0, so my inverse exists and I can go ahead and move forward. To find the adjoint matrix for a 2x2, you go ahead and switch these two, so -4 and the 1 switch places, and then the other ones change their sign. So the 3 becomes -3 and the 6 becomes -6. Which means A inverse is going to be 1 over -22 times this matrix. And you can go ahead and multiply that fraction through, but I'm not going to. This is about as simplified as you need to make it. Okay, that's what it looks like for a 2x2. This week we're going to expand it to be greater than a 2x2, talk about 3x3s, 4x4s, and really go on for any other size matrix. So our process still holds. The first thing we need to do when calculating the inverse is to calculate the determinant. Then, if it's not 0, then we can go ahead and move forward. If it is 0, that means A is singular or non-invertible. You'll see that error in MATLAB a lot. Matrix is singular. That just means that determinant equals 0 and the inverse doesn't exist. But as long as the determinant of A is not equal to 0, we're good. We can go ahead and move forward. Calculating the determinant for any size matrix can be done using something called cofactor expansion. And it can be done along any row or any column, and I'll talk about that. So first things first, the cofactor is called the signed determinant of a smaller square matrix found by removing rows and columns of a matrix. So let's say A looks like this. If I remove a row and a column from A, let's say I remove this row, this column, that leaves me with a square matrix left over. The determinant of what's ever left over is called a cofactor, and the sign on that value is changed based on this grid. Okay, so let's go ahead and look at how to calculate a cofactor quickly based on this matrix. So let's say I want to go ahead and find C3, 2. That means I'm going to remove row 3, column 2, and my leftover values are going to be 1, 6, 3, -2. If I find the determinant of that matrix, that's going to be my cofactor. So I get 1 times -2 minus 6 times 3, or -20. That's my cofactor. However, my sign on my cofactor is modified based on this grid. So this grid always starts with a plus in the top corner, and then it alternates plus, minus, plus, minus, plus, minus. If there's a plus, that means you don't change the sign. If there's a minus, you do change the sign. So this is cofactor 3, 2. So in the 3, 2 location, I have a minus, which means I'm going to change the sign. So this cofactor now goes from a -20 to a +20, and there's my final cofactor. And we'll look at calculating lots and lots of cofactors, but essentially the process is this. You remove the row and column that the element is located in. So 3, 2 means you remove row 3, column 2. You're going to calculate the determinant of the remaining values in the matrix. So remove, calculate the determinant, and then adjust the sign based on this grid. So let's go ahead and do one more with this matrix. Let's say I want to do cofactor 2, 1. That means I remove row 2 and I remove column 1. My remaining values are going to be 2, 3, 3, 5, and keep them in the same orientation. So my determinant is going to be 2 times 5 minus 3 times 3, or 10 minus 9, which is 1. Then if I go over to my grid here, in the 2, 1 location, I have a negative sign, which means I change this from a positive 1 to a negative 1, and there's my final cofactor for 2, 1. So C2, 1. The cofactors corresponding removing row 2, column 1. That's your process. So finding the determinant using cofactor expansion is essentially you're going to pick one row or one column. And if we find all the cofactors in that row or column, then we can go ahead and do cofactor expansion. Okay, so let me have A again. Let me just copy and paste it down. I want to go ahead and do cofactor expansion in order to find the determinant of this matrix. I'm going to go ahead and pick a row or a column. Generally, you pick the row or column that has the most zeros. I'm going to go ahead and pick this row. It's the most common row to be picked, row 1. I'm going to go ahead and find the cofactor for each element. So that means I need C11, C12, and C13. So I would remove row 1, column 1, then I'd remove row 1, column 2, then row 1, column 3, and keep going until I have removed all of the rows, all of the corresponding rows, all of the corresponding columns, and found my determinants. Notice for this one, there's 3 elements, so I need to find 3 cofactors, each one in my row. Keep in mind, you need to adjust the sign. For this row, the sign adjustment will be positive, negative, positive. So don't change, change, don't change. Then we can go ahead and apply this formula. This formula just states that we're going to take all of our cofactors and multiply them by the corresponding value in A. Then add it together. So essentially, to find the determinant of A, it's going to be A11, or the element here, times cofactor 11, or the cofactor where I remove the row in the column, plus A12, so this number here, times the cofactor, where I remove the row and remove the column, plus A13 times the cofactor. So I take each of these numbers, find their cofactors, multiply those together, and add them all up. That's how you would do cofactor expansion. And the process holds for any row or any column. It doesn't matter. So I could do it with this column instead, and it could be A12, C12 plus A22 times C22 plus A31 or 32 times C32. It doesn't matter. You can choose any row, any column. You will get the same answer. Okay, so that is cofactor expansion. We'll go over lots of examples, or a couple examples in class. The alternative, there is an alternative way to do it with a 3x3. Cofactor expansion works for any size matrix. You just keep having smaller and smaller determinants until you get to 2x2s, which are easier to find. But if you have a 3x3, there is a shortcut method in order to find the determinant, and it looks like this. So here's our A matrix. What we're going to do is we literally just copy the values over. Put them right next to it, and then we are going to essentially do the fish method for a 2x2, but now applying to a 3x3. So we multiply these numbers together, multiply these numbers together, multiply these numbers together, add them all up, and then we do the other diagonals. So multiply these ones, multiply these ones, multiply these ones, and then we add those all together, and then we subtract. So it's essentially these numbers minus, minus these numbers. Same idea though, but now we have 3 diagonals instead of 2 diagonals. Or we have 3 sets of numbers per diagonal, but there's the same fish method. Okay, for a 2x2, it's real simple. For a 3x3, it still is pretty simple, but it is a little bit different. But it is a nice method that we can use for a 3x3. You can use either one, cofactor expansion or this method, but only for 3x3s. So we take these numbers plus these numbers, minus these numbers, plus these numbers, plus these numbers. And that's outlined here. And like I said, we will go over lots of examples, or some examples in class that illustrate how to do this.